When I teach, I think it is even more important than teaching the material to convey your own personality, to convey your personality as a working physicist. I think what young people need are role models, people they can identify with in terms of the passion they have for their subject, or the intensity, or the way they think, the way they analyze. That's, I think, what young people have to learn. But I think if you see young children, whether they play with stuffed animals, whether they read books, or whether they want to work with tools, the children are expressing something about their preferences. I think when you're a child, you don't really know what science is, you don't know what mathematics is, but one aspect is playful exploration, and then another aspect is you take those subjects in high school, and I always liked physics and mathematics the best. It was clear for me from the beginning that science has an experimental side, and what actually drew me into science was both my love for mathematics, my love for abstract thinking, but also I love to tinker, to play with things. I had a motorbike and I was repairing it and doing some modifications. I had a chemistry set, so I was exploring science on the hands-on side, and I enjoyed it. Actually, I was quite interested also in a career in mathematics, and I just felt that physics would connect me more with the real world, and the real world also means the possibility to do hands-on work. On the other hand, this interplay between experiment and theory during my career has taken a few turns back and forth. For instance, at the end of my undergraduate studies, I did a purely theoretical master thesis. So at that point, I actually wanted to become a theorist. First of all, most of our education is theory-based. In high school, at least at my time, we hardly had any lab classes. So it was all teaching, understanding the concepts. And also at the university, sure, we have the equivalent of junior lab, and so we went through those lab courses, but the far dominant portion of the education is actually more conceptual and theoretical. I remember when I took lab classes and there was some torsion pendulum, I was just fascinated by that. I could play with that. I was experimentally realizing what was in the differential equation. So I really felt I wanted to feel physics, I wanted to see physics, but nevertheless, a couple of years later, I picked a theoretical topic as my master thesis. I think I was always fascinated by the power of describing nature. And when I learned about statistical physics, I found it fascinating that you can make a few assumptions about what atoms do, kind of some probabilistic arguments of entropy, and you can deduce the equation of state of the whole system. So by just very few assumptions or very few things you can deduce a lot, and that fascinated me. So therefore I decided to work on a theoretical subject for my master thesis. I fully agree. It is the style of my group to push the frontiers of the field. I tell all the students who work with me or who want to work with me, if you want to work with me, you have to be a hardcore experimentalist, because our job is to push the boundary of what is possible. So my group is extremely focused on doing new things, doing things which currently seem impossible or out of reach, but bring them into reach. Well, I found it, and I still find it fascinating, that when you look for a spectrum of an atom or molecule, that you can learn all the details about the atomic and molecular structure just looking at the frequencies in the electromagnetic spectrum at which the atoms or molecules resonate. So I was particularly excited about it when I, during my PhD, discovered a new molecule and there was hardly anything known about it. And I had a spectrograph. I looked at the light which was emitted by the molecules, and it were hundreds, if not 1,000 of different spectral lines. And a lot of them were not regular. It didn't make any sense initially. And it took me, I think, about 2 years or so to solve the puzzle. So I had to learn a lot of theory, I had to do a lot of computer simulations. I had stacks of papers of simulated spectra, just trying to find a simulation on the computer which became similar to the experimental one. The molecule was helium hydride. It was a molecule consisting of the 2 lightest elements in the universe. So it was a very special molecule. And after 2 years, I had found the code. I'd really deciphered the code of nature, and for the first time I knew what is the size of the molecule, how stiff is the bond between the helium and the hydrogen. So all the basic questions you ask about a molecule, I could answer. I found it extremely fascinating to be able to do that, and it was even more fascinating for me since I worked at an institute which didn't have the tradition of doing that. So almost everything I had to learn by myself or learn by asking other people, learn by reading the literature. I think it was a very important step in my development as a scientist. So that is actually an interesting story. If you allow me to fill in some gaps, we've talked about spectroscopy, which was my PhD work and the work I did during my first postdoctoral appointment, still at the Max Planck Institute. And I've also expressed to you the fascination and also the satisfaction I had in analyzing a brand new molecule. On the other hand, I felt after 3 years as a postdoc, I was sort of at a dead-end street because this kind of molecular spectroscopy, most of that was done, early on, and there were not many molecules left over to do that kind of analysis. And also the frontiers of the field were different. So I felt the molecular spectroscopy I did was neither applied nor fundamental. And I felt if I wanted to make an important contribution to science, technology and knowledge, I should either do something which is clearly applied or which is clearly fundamental. So I was at crossroads. And I decided to work on an applied project because throughout my studies as an undergraduate student or also during my PhD, I always wanted to do something more applied. Applied means something which is more directly related to the needs of society or the burning questions which we have to solve as a nation. One of the needs of the society is to protect the environment, to avoid pollution. And I felt as an atomic physicist who understood spectroscopy, there was an opportunity for me to contribute, namely to work on using spectroscopy to monitor combustion. So I went into combustion diagnostics. So I used my knowledge of spectroscopy and applied it not to new and potentially esoteric molecules. I applied it to flames in a Bunsen burner, flames inside a diesel engine. So my goal was, and this is what I picked as my second postdoc, and at that point I intended to make it my career, to use lasers and spectroscopy as a tool for cleaner environment, to make combustion more efficient, to make combustion cleaner. For a lot of the work you can use commercial lasers, but you either have to adopt the lasers to the special purpose or to do some modifications. And during that year in Heidelberg, I worked with ultraviolet lasers, and one of the was probably not an earth-shattering idea, but a nice idea I had is to modify a laser from a single wavelength into a dual wavelength laser. And with that, we had a 2-channel capability, which meant we could monitor two chemical species simultaneously. So that was a nice development. It was a fun for myself and for the people around it. We even took out a patent. I think in the end it didn't really have a big practical impact, but that was sort of one example where you want to improve your tools, or you want to really master your tools in order to use them for your scientific purpose. So while I worked on combustion research and worked on applied research, I learned a lot about myself. I saw on the one hand the deep satisfaction to work on problems which are so self-evident somebody has to work on it. But I was missing something. I was somehow missing the long-term challenge. I was working on problems and solving problems, but I felt the desire to work on problems where you don't even know if there's a solution. So I really felt, while I did this applied research, I want to work on something else. There was also one other thing I learned. I felt that applied research was more directly contributing to the solution of problems I identified with. But while I did the applied research, I also realized how much applied research draws from fundamental research. So laser cooling was already developed quite well at that point, but I felt there was a big potential to study the properties of laser-cooled atoms and explore, other science with cold atoms. So I decided that is the most exciting field I can contribute to with my tools in fundamental physics. And so what I did is I sent letters to some of the best groups all over the world and asked if they would offer me a postdoctoral position. And eventually Dave Pritchard here at MIT offered me such a position, and that led to the fact that eventually in early 1990 I arrived at MIT. Lasers are, of course, a directed form of energy. If you hold your hand in a laser beam, you feel the heat. Because the light, the photons, which is energy, are absorbed by your skin, are converted into random motion, and we feel that as heat. Well, with some of the lasers we have in our labs, you can even burn your flesh. So this is how lasers heat. But if you apply laser radiation to atoms, there's one important difference. The atoms cannot keep the light. When atoms have been excited to a more energetically higher state, they have to re-emit the photon. So a photon which is absorbed with 100% probability is re-emitted. So therefore the energy which the atoms absorb is emitted again as fluorescence. It's quite fascinating how that comes about. So what happens is we need a frequency shift of the light, but in its simplest form, this is just provided by the well-known Doppler effect, which makes the frequency of light depend. If a moving object emits light, the frequency depends on the direction of emission, and that is sufficient to make lasers cool. I was 2 years into my postdoc, and we were laser cooling atoms, and we used this new idea which myself and Dave Pritchard has come up with. And what we saw was completely pitch black clouds which just absorbed all the light completely which we are sending at them because they were so dense. So we had reached higher density in large clouds than anybody had ever reached before, and very soon it became clear that this could bridge the gap. And what then happened was also a formative moment. We started then to discuss what can we do next. And it wasn't first very clear. Dave Pritchard had worked out all these ideas about how to form cold molecules from cold atoms, and myself as a postdoc, I said, well, why don't we go for the holy grail? Let's combine laser cooling and evaporative cooling. There is a chance that it will work. And I will never forget that after a few such discussions, Dave Pritchard just said, I let you do what you want. So Dave Pritchard had really the greatness of abandoning his own ideas. Some other people got famous with these photo association, putting cold atoms, associating cold atoms into molecules. Well, everybody was delighted. I remember the moment we saw it in the lab, which was full of tension and anxiety. Well, the situation was slightly more complicated because for over several years, actually for probably about 3 years or so, before Bose-Einstein condensation happened, my group was in a head-to-head race with my colleagues at Boulder. And the group in Boulder had actually, in the summer of '95, pushed ahead of us. They had actually observed Bose-Einstein condensation in June of 1995. So when we discovered Bose-Einstein condensation in sodium, that was in September, so 3 or 4 months later, I think the first reaction was big relief, because we realized that Bose-Einstein condensation would start a new era in atomic physics, and we were of course afraid that with our atom and our techniques we may have bet on the wrong horse. And so we were pioneers of the field. I had put all the resources into the pursuit of Bose-Einstein condensation, and we came very close. But there were a few moments where we were afraid of missing out on all the excitement. So when Bose-Einstein condensation finally happened, it was probably more, the immediate reaction was the big sigh of relief rather than the excitement for new discovery, because the first observation had been made a few months earlier. Well, to some extent I have detached myself from the goal by a time scale which is maybe 20, 30, 40 years. I think the work I'm doing right now is fundamental. It improves our understanding of matter. It leads, in conjunction with theoretical colleagues, to an improved description of matter. But right now, the matter which we use as a test object to observe and understand new phenomena is sort of so cold and you can say so special that it cannot be used for anything applied. On the other hand, a better understanding of materials should lead to novel materials and novel devices in the future. The support and mentorship I had as a young scientist and as a young professor here at MIT was really almost unprecedented for me. So, there is the issue of lab space, but what came even earlier was the generosity of my mentor and postdoctoral advisor, Dave Pritchard. Dave Pritchard has been a pioneer in laser cooling, and in collaboration with me as a postdoc, things were even pushed further. So Dave Pritchard at this point had 3 experiments in 3 different subfields of atomic physics, and it was probably clear at this moment, but definitely clear in hindsight, that the laser cooling experiment was his most promising and best experiment. And when there was a possibility that I would join the faculty as an assistant professor, he told me that, well, he didn't want to create a shadow problem, that I would do laser cooling in his shadow. And he told me if I were to stay at MIT, he would get out of laser cooling and hand me over all the experimental resources. This is a highly unusual offer, almost unheard of, that a creative, active scientist is giving up is getting out of the field he has helped to create, is handing over his best experiment, his best lab to a young assistant professor. And at the same time he told me, but this is your own experiment, we will not publish papers together. You can ask me for advice, but I want to make sure that you have your full independence. And I know there was one of these still memorable discussions. I sat down with him and told Dave all about my uncertainty whether I would succeed or not. I told him that I'm here with, children and a German wife. I can't even say for sure whether I will stay forever at MIT or in this country. And Dave just said, I know all about that, and all I expect from you to work hard and continue what you have done. So he took all the pressure off my shoulders and just said, well, just go with it. And what happened is almost history. 2 years later, my group had realized Bose-Einstein condensation. If I had started at any other university, I would not have been able to build up a lab in 2 years. So after 2 years, my group contributed to one of the most exciting developments in physics, and we were right in the middle. So what I did at that point, I had actually thought Bose-Einstein condensation could motivate me for my whole lifetime. I would get colder and colder and study this and that this is sort of the big goal which keeps you focused on good science for years and decades. But after 2 years, I was there. So I went actually to Dave Pritchard and said to him, I would not have done it without you. I was to some extent executing ideas we had developed together. I was taking over the lab from you. I want you to co-author the paper. It's one of the most highly cited papers in physics. And Dave said, after thinking about it for a moment, he said, no, I want you to take the full credit. So I still feel that what Dave Pritchard has done for me, how he has supported me and mentored me, was highly unusual. And there were moments it was just difficult for me to even understand it. So let me try to use the words which Dave Pritchard used to explain his magnanimous behavior. At some point he said, well, I gave up an experiment, but I got a wonderful colleague at MIT. At another time he said, well, and which I think it's just wonderful expressing kind of the feelings. He said, well, he said it in a speech. He said, I gave Wolfgang the keys to the family car because he could drive it faster than I could. So family car, sort of the two of us being, a couple for so many years, collaborating on various levels, has really been a wonderful experience. The value of enjoying science and being excited and using that as one of the, one of the most important motivations, I think, is true. I think the special circumstances of supporting somebody are really unusual. I think the atomic physics group at MIT has, with Professor Kleppner, Pritchard, has sort of this wonderful tradition and history, and it's a very, very friendly family. What was very satisfying for me after I was established and became as famous as Dave Pritchard, or to some extent even more famous, the two of us could collaborate again. So Dave Pritchard told me we won't publish papers together because he wanted me to get fully independent, but then as two independent people, we have now worked together, jointly supervised students for about a decade. And in a way, what I also find remarkable is that initially, he, of course, had pioneered the field. He taught me many things. He mentored me. But right now, Dave Pritchard is very focused on educational science. So he doesn't really have the capacity to, run a lab completely by himself. But in collaboration with me, he can still do wonderful physics. So it's for me almost like a life cycle of the two of us have always been a team. A team when I was a postdoc, a team when we were independent, but had independent research groups, but there was a lot of advice and camaraderie, and now we are collaborators again. It's just those life cycles. And one way how I was able to express what Dave had done to me was when we came back from the ceremony in Stockholm. We were back at MIT. I went to his office and gave him the original of the Nobel medal. I told him I couldn't share the honor of the Nobel Prize with him, but that he has been a big part of it, and this is how I want to express it. And I know it meant a lot to him. You react with joy, with pride for MIT, for your collaborators, for yourself. It's a wonderful acknowledgement, and yeah, it's very, very special. It's sort of great. I mean, you're struck by it, you're hit by it. It really brings together the whole community. It also brought together the whole field, because for Bose-Einstein condensation, the Nobel Prize was given only 6 years after the discovery, and the field was in full swing. So everybody who was working in the field felt elated, because the whole field became distinguished as one of the important frontiers of physics. Dan Kleppner was the PhD advisor of Dave Pritchard, and I felt to some extent the way how Dan Kleppner was educating and Dave and nurturing his career and allowing him to become independent and famous, that this sort of repeated itself between Dave and myself. Now Dan is sort of the senior member of the atomic physics group, and I've appreciated his, the science he's done. He has sort of enormous scientific skills. He has shown great taste through his career. He has worked on many important frontiers. But he also has this wonderful, balanced personality. And when I was an assistant professor and I felt I was in competition and just needed his advice, he always gave advice. So his balanced personality and his friendship and his calmness were very, very important. I felt as a young assistant professor I had this dynamic environment at MIT with all these wonderful students, but with my two mentors, Dave and Dan, I also had the experience, the tradition and the wisdom. And I felt when I was a professor, but there were situations I just didn't know what to do. I needed a sounding board, and I always found it. Well, Martin is just a bundle of energy and joy. He can be excited about physics, he's understanding physics, he conveys physics. You just realize that everybody who's working with him is pulled along by him, or even more positively, he brings the best out of people. But you really realize that after he came back to MIT and started his own lab, the sort of level of liveliness and energy and excitement in our hallway has increased. Even if somebody would offer me to opt out of teaching, I would not take this offer. I want to teach because it keeps me grounded, it keeps me connected to the basics, but also it forces me to again and again present the logical structure of physics and the basics of physics to learning students. I think it is this deep understanding. When I teach, I think it is even more important than teaching the material to convey your own personality, to convey your personality as a working physicist. I think what young people need are role models, people they can identify with in terms of the passion they have for their subject, or the intensity, or the way they think, the way they analyze. That's, I think, what young people have to learn. So when I'm in the classroom, I sometimes like if a question puts me on the spot. I may not know the answer, but I have to derive it. I'm struggling, I'm reiterating. But I show my thought process to the students, tell them what I check out, how I maybe construct the answer of something I know, and then add something I have to think about it. I think to present yourself as a working physicist to the physics student is important. I think what I think showcase here for MIT is this kind of mentorship. I mean, there is something about, I know that in the physics department, we rarely hire senior people. We want to, nurture ourselves young talent. So almost all the hires in our department are done at the assistant professorship. So we want to identify talent early on and then nurture and develop it. And a lot of the people have become, well, the stars in their fields. And also, many of them have stayed at MIT for many more years or for their whole lifetime. So this focus on young people and introduce young people or bring in young people to MIT and make sure they succeed, this is really an MIT tradition. I may have experienced that in an even more unusual form, that Dave Pritchard was stepping back, was handing me over the experiment. But in a way, what I experienced in that form really reflects on the culture which we have in the physics department. When I received the Nobel Prize, I shared it with two of my colleagues and competitors in Boulder, Eric Cornell and Carl Wyman. But it's interesting that Eric Cornell was a graduate student of Dave Pritchard. He left shortly before I arrived. And Carl Wyman was an undergraduate student with Dan Kleppner. So it's clear that, and there are other very famous people in the field who have really been educated by Dan or by Dave. So Dan or Dave have really created a family of atomic physicists, and their impact on the field cannot be overestimated.